we talk about finding co-founders. So about 5 years from now, I also found co-founders in some event like this, and all the problems that they made me go through. That is what we will talk about. That's the story. That's the big part. So going ahead. So we are a startup. We are called ISOView. It's a banking as a service startup. This may sound similar. You may have heard of infrastructure as a service, platform as a service, then what is banking as a service? So what banking as a service is we are a backend to a lot of fintech companies, right? So whenever you have a fintech company, all that you do is there are two kinds of transactions that you do acquiring transactions, you do issue transactions, right? Either you issue a card, you open a bank account, you give out a wallet. So these are what you call issuing. Or on the other side, you do acquiring. You collect a payment, you collect a card payment, you collect a UPI payment, and different kind of things you do. And at the end of it, any fintech, they may claim to do anything. At the end of it, they will have to go and interact with the bank, because only the regulated entities, REs, what the RBI calls, can only connect to the card networks to any kind of payment intermediation. So we as a company, we provide a layer of technology where if you want to build a fintech company, you can come in, just consume our APIs and SDKs, and you are done. You do not have to worry about PCI-DSS, you do not have to worry about data localization, any of these regulations you don't have to worry about. We have pre-authenticated, pre-authorized, CISO regulated stacks available from various banks today. There are 9 banks we already work with, including some of the PSU banks, and you can go ahead and do that. So that's what we do. But because of the kind of things we do, there are innate problems with it. And what are the problems? One of the largest problems is this, is in every transaction we make money. Only when transactions happen we make money. Only when you pay money we make money. Only when you deposit some money into your bank account we make money. If you do not do anything, if we have a customer who just keeps on opening the app but doesn't do anything, our APIs get called, but we do not make any money on that. So we are tied to making a small bips, and how much money we make. Like you might be transferring 10,000, 15,000, or thousands of dollars even, but we make in small bips, right? And hence, and that creates a complication in the problem. We have to provision infrastructure, provision the tech for doing non-financial transactions also, while we make money only in financial transactions. So back when we started with a very typical way how you would build when you're a startup team. We were a team of about 7, and we went in, and in Java Spring Boot, we wrote this middleware, and this is what we call a banking middleware. And why Java? Java is because inside of a bank or anything you need to do with financial technology, you require a lot of encryption, decryption, and also there are a lot of standardized methods of application, and ISO 8583 is one of them. And this standardized methods of communication requires a lot of demugs and knocks. So what is this standardized methods? So normally when you will call an API, what you will do? There will be a certain set of parameters, let's say 10 parameters, you push in those parameters, then you make a gRPC or an API call. But that's how you, but the banking systems do not interact like that. You have to package this in a certain byte string format. Then we open a certain channel into the bank, we keep on writing into the channel, and we keep on hearing on the channel. So, and let's say we do 1,000 transactions per second. So we have a channel open, and every second we are writing 1,000 transactions to it. We have a different channel where we are receiving this transaction, and all this is byte string. So we have to take the request, convert it into byte string or ISO format, and then we'll receive in the ISO format, we'll have to debug it, and then we realize what is the value. If it is a successful transaction, it's a failure transaction. And the reason it is done is we are transferring large amount of data in very short amount of time. For example, the amount of time it takes from your card being swiped to you getting a success or failure has to be within, for Visa standard, let's say, has to be within 12 seconds. But in between, there are about 30 odd service calls that are made to various agencies. There is a fraud call that is being made, there is an acquirer call that is being made, there is an issuer call that is being made. To your CBS, it is checked if your debit card has money or not, if your account has money or not. So all this has to happen so fast, and hence the data compression is required, and that's why there's this requirement of a middleware. So we developed this technology. It was in Java Spring Boot, and it worked for some, because that point of time we only had 2 customers, and 2 customers was doing very limited number of transactions. And fintech as the industry didn't evolve at that point of time. The real fintech upload happened somewhere late 2019, but before that nobody cared. Like we were like a boring startup at that point of time. So this was our architecture, and that's why we were serving, which was working fine enough. And at this point in time, we are not on cloud also. We were hosted on a SIFI data center in Mumbai. And the reason we did that is that data center was co-located with other banks' data centers. So we were reducing our network hops. So now, as we grew a little bit, we got more customers, and we got some large NBFCs that came in. And when the large NBFCs came in, this track didn't work anymore. And then we did some stupid kind of a solution. We said, okay, one core is not working. We put in a load balancer and a manufactured load balancer, not what you consider to be a typical cloud load balancer today. So we procured a load balancer, we put it in, and then on the load balancer we added. So as the customers would increase, we would add just one more node into it. So where we would copy all the same code, we'll add one more node, and we will keep the database constant. And on the database, we were just adding more slaves as the requirement went in. But this had its own challenges, own challenges as in so every time we said we will add one more node, and the way data center pricing works is this. We will only need the full power of all the nodes at our peak hours. And our peak hours are the hours when the banks are not open. Right? For example, we see most of the transactions coming 8 a.m. to 11 a.m. because suppose that the banks are open, so people go to the bank. Because agency banking segment is one of our largest segments. Agency banking meaning where you go to a BC center, which is not a branch, and do some transactions. That is called agency banking. And almost India's 80% agency banking providers use our software at the back end. And as a result, our peak time is between 8 a.m. to 11 a.m. And after that, we have a lull. And then 5 p.m. to 9 p.m. is where we see another peak. But we were having to provision in our data center servers for the peak time, where 90% of the time we are not using them. And hence it was adding to a cost. And when you're playing in a business which is such low margin, that doesn't make sense. So then what we did, then we went in, and there was pressure on us to reduce the cost to achieve profitability, because at this point of time we also were talking to investors. And so we decided we should do a microservices. And when we decided to do microservices, we saw our stack, and we realized that not all of it what we do is banking. Banking is about 30% of it. We are interacting with the bank only for 30% of the things. And about 70% of the things is we do internally. For example, fraud check. We do not talk to the bank to do the fraud check. We have our own fraud engine. We have our own fraud ML engine. And these two interactions is what we are able to analyze if something is a fraud or not. We do not have to talk to the bank. We had a BI analytics engine. We never had to talk to the bank about it, because that's a post-transaction. After you do the transaction, then we are pushing into the warehouse, and then we are reporting it. So the bank had nothing to do with it. But then we had, in a single stack, in one monolithic application, we had everything of it. Then we had a notification engine. So especially when you do a bank transaction, you would receive a SMS, you could receive a WhatsApp, you could do an app notification in your Android app, and most of our customers want all this sophistication. So we have a very evolved notification engine, and nothing of that had to do anything with the bank. So when we found that out, we said, okay, we'll separate all these individual things into different operations. And in addition to that, it also helped us in doing one extra thing, which is, this is the time which was like around the pandemic. And when the pandemic came, hiring resources became a problem, because we are a company based out of Bhubaneswar. We have about 350 people in Bhubaneswar. The tech team is based out of Bhubaneswar. The company is based out of Mumbai. But finding people in Bhubaneswar became very hard, and especially if you had to find all 300 people who are Java engineers, that was much more harder. So then one solution we figured out that if we can separate all the stack, we can develop this in technologies where we can find developers. So we could use a multiple bunch of technologies, and then we developed the stack. But then we didn't have deep infrastructure background, so whatever we had learned earlier, we tried to replicate the same. So we created 7-8 microservices, but then the way we would deploy it was very similar to how we were deployed earlier. We just went in, and whenever the request would go in, we'll add one more node. And that's what I'm sure anybody who is doing a startup, anybody who is working in a small company, they would be doing that way, right? So we did it. And then the problems that we tried to fix initially, over a period of time, we again got to the same problems where we are having to add hardware, which we are not using most of the time. And with it, the cost kept on increasing, because now earlier we had one service, and not to one service we were adding hardware. Now we had 7 services. So to 7 services, individual teams were adding hardware. So the hardware bill became like 7 times of what it was initially. Then we had to dive deeper, and around this time we made a decision, because at that time there was a RBI regulation change where some part of your financial application, they came up with this data localization rule. Data localization rule is the banks didn't care anymore if you did some part of your operation outside of your data center, of your certified data center, as long as your data, you are guaranteeing that the data has to reside in India. And if you remember, this is around the time when MasterCard was banned in India, because MasterCard was transferring data to UK, right? So if you got a certification, and there are various certification agencies, you can go to them, they will certify that you are not transferring any data outside, and you can use the cloud. Or you can put some data in the cloud. And then we took this decision that we have to use a cloud, and we started using Google Cloud as well. Google Cloud. And when we said Google Cloud, not a typical Google Cloud, we had servers in our data center. We said, okay, what is the equivalent of a server in the cloud? Is a compute engine. So we went in, we copied our Linux machines into a compute engine instance, right? So not typical cloud. So we had a WAF load balancer. Instead of load balancer, we started using a cloud load balancer. But the full power of the cloud didn't come to us yet. And this is when we dived a little bit deeper. And and we started understanding our individual pieces of this product, the 7 things of the product, more deeply. And we try to see how best we can leverage it. What are the things we need to do post-transaction which has to be real-time, which do not need to be real-time, and then we will try to build an architecture around it. So this is like a typical workflow of a fraud analysis. And each of this today, what we have done is built into an individual microservice, right? Individual microservice using PubSub as a service bus, Google's PubSub as a service bus. And what we were able to achieve with that, we were able to use a bunch of technologies together. Like today in our stack, we have about 7 languages that we use. And the reason is we could find engineers, we could hire, and individual pieces became very, very simple. And we could just hand it over to these micro teams who can do their own technology, hire their own people, and just run out of it. So that's the first advantage. It solved hiring problem for us. The second problem it solved for us is initially we were running on licensed databases. Right? We had Oracle, and there was a database called CockroachDB. We had licensed instances of this. And mostly because we came from the Spring Boot world, and a relational ORM was what was fitting for us. But we realized that for all of this, a relational database is not the best thing. For example, if we are doing a large number of transactions, we'll be writing a large amount of data. We may not be querying the data at all. And Cassandra, for example, is optimized for writing but not for querying. So, and it is also fail-safe. You can deploy it in across multiple regions, and get more reliability out of it. So the kind of tools we could use to achieve our goals, that our palette increased of what kind of tools we can go back and use as a result of this. So then what happened is we at the end of this exercise which we went through for about 8-9 months, we finally ended up with 700 plus microservices, right? And the 700 plus microservices, again, it became another nightmare to manage, because people were going and creating a compute engine and putting their own microservice, and that's what they were serving on their own load balancer. That was not sustainable anymore. And so we dug a little bit deeper, and Kubernetes was a technology that was not well documented, if you see in 2019, but the documentation was evolving, and as the documentation evolved, we were able to train our team into that. But in addition to that, what happened around mid-2020, Google Cloud also came up. The beta release, there is a beta release of Cloud Run. So what Cloud Run is where you do not understand what Kubernetes is. Google does all the management of the Kubernetes, but they are giving you an interface to deploy something into Kubernetes. So all the control plane activities, if anybody understands Kubernetes, all the control plane activities you do not have to deal with. You only deal with your code, how you deploy your code, and what will be the endpoint of it. Google deals with all of that, and it is connectable to load balancers. And if we could do that, we could migrate our IP, so we didn't have to change any of the stack which was consuming it, but we were able to put small pieces of that into Cloud Run. So initially we started migrating all the post-transaction activities into Cloud Run. And what it did, it reduced our cloud bill by 50%. 50%. It just lasts for in a particular month in 2020 February, we were paying about 22 lakhs per month. That was our bill. And in August, it was about 9 lakhs per month. That is when we had migrated a bunch of it reducing cost is basically your bottom line. So once you reduce your cost, you'll be profitable. If you cannot reduce the cost, the amount of money that we make on each transaction is so small that you'll be going into a loss. So we started investing heavily in understanding Kubernetes and how it works. And in addition to this, let me also tell you some of the necessary evils of being in fintech industry. Okay, anytime you work with a bank, okay, they will also come and audit you, and they will audit you for three things. Number one, they will audit you for your security, that you are 100% secure, nobody is able to attack and steal some customer data from you. Number two, they will audit you 100% for a DCDR. And what is DCDR? So you need to have a primary connectivity. Okay, you also need to have a secondary connectivity, a secondary center, so that if something happens, there is a natural calamity, and the secondary center again is needed to be in a different seismic zone. Like for example, one seismic zone is Mumbai, the other your DR, your disaster recovery cannot be in Mumbai or in Tamil Nadu, because that's the same seismic zone. It has to be a different seismic zone, and they will audit you for that. And the audit is if your data center goes down, in how much time you are able to bring up the services in the different data center. And the TAT for that, the maximum TAT for that is 2 hours, which is big enough of a time. Like let's say you are a user, your bank went down for 2 hours. Will you be working with it? You will not, right? But today, if you see the most modern banks, like for example, IndusInd Bank, I understand is a modern bank. ICICI is a modern bank because the technology they use. Their TAT is about 30 minutes, right? But by using Kubernetes and the way Kubernetes works, so how Kubernetes works? For a very simplistic understanding of Kubernetes, is there is a control plane. Your control plane is what controls what is to be started, what is to be stopped, what will be the IP routing of it, who this request to be sent to, and then there is a data plane. Data plane is where your processing actually happens. Your pod comes up and your processing actually happens. So initially for our DCDR setup, what we used to do is we used to maintain a complete setup in Mumbai, in Google's Mumbai zone. We also used to replicate the same setup using Terraform in Delhi zone, and we would keep it running all the time. And when we keep it running, we have double cost. Instead of the same cost, we have to pay twice. Because if we do not keep it running, we just boot it up when it is required, then Google has provisioning issues also. Like if you require a bunch of services together, they will not be able to provision together. You have to do a request, they have to approve, only then it will happen. So then we will not be able to meet our TAT, the reboot TAT of about 30 minutes that which we had decided ourselves. So we will not be able to do that and will fail audits. So what we used to do is to run this hot instance. It was an active kind of instance, and we used to run it all the time, and we used to incur cost of it. But what Kubernetes was doing, Kubernetes is you have a controller. So once you have a control plane isolation where all your traffic goes in and they decide where the traffic should go to, now we could do an active and inactive kind of a DR, and we didn't have to manage it. That was the beauty of it. For example, so Kubernetes, everything you run in Kubernetes, a single process is what you call a pod, right? A pod runs inside a node. Node is what is your hardware, right? Let's say you have 5 servers, that means you have 5 nodes. Within these 5 nodes, you could run 1,000 pods, right? Consider pod to be a virtual machine, or somebody who understands container, consider a pod to be a container. So each pod is a container. Not exactly, but think of that if you are familiar with that. So in a single node, there can be multiple pods, and if you say multiple pods, that means you can run multiple services. So let's say all our 700 microservices, we could run in a single pod, because not everybody will require the computing at the same time. I'll give you an example, reconciliation. Reconciliation only happens at night, and at night, no transactions happen. So if reconciliation requires a certain amount of computing power, we can put it in the same node where transactions are happening, because when transactions are not happening, that time reconciliation is happening, right? So essentially we were putting all our 700 microservices or microservice pods into about 3 nodes which were in Mumbai, and we had provisioned one extra node in Delhi which was not actively running. Only when the load in Mumbai was exceeding, when the control plane was figuring out that the load parameters in Mumbai was exceeding, then it would go to Delhi, and then the request would get processed from here. And Delhi was an auto expansion node, so if it couldn't handle, it can replicate itself as you go over. So what it did, it immediately reduced our DR cost to 0, because this node was not an active node. and we could provision it in real time without having to ask Google to provision it for us. And it worked. And we were able to even reduce our TAT, the turnaround TAT after a disaster recovery exercise, to about 7 minutes. Just 7 minutes we are live in it, right? So that is the advantage it brought. So as we started working on it, initially because most of the 700 services, they would not be very high frequency services, because initially we only migrated low frequency services. So a single pod was working. A single pod mostly would work. And this was the structure that we did, which I spoke about, that we had a number of nodes in Delhi, Mumbai, and a DR node in Delhi. And we could route traffic as we wish to Delhi, Mumbai, whatever. We didn't have to incur much cost of that. Now, but when we added this auto-scale mechanism, we said, okay, if the pod is loaded, and that is when we migrated our transaction engine to Kubernetes. When we migrated our transaction engine to Kubernetes, transactions, we get 20 lakh transactions a day. So that's a lot of transactions. All these 20 lakh transactions cannot be processed by a single pod. So we added autoscale, and the autoscale would add multiple pods, but then we figured out there was a traffic pattern. All the requests were still going to one pod, right? And what is the reason for that? So our APIs, or how we interact between applications, once you hit the load balancer, from the load balancer backwards, is all gRPC. And the reason it is all gRPC is we want to make it fast, so we do not terminate transactions. And how gRPC works, for people who do not know, a simplistic understanding is a typical HTTP request, a REST call. How does it work? You go, you find a resource, you look it up on the DNS, you establish a connection, you get an acknowledgement. Only when you get an acknowledgement, you post your data. After you post your data, you get a status, 200, 403, whatever that is, and then after you get the final status, you will get a, if you understand Wireshark, and you would see, you will get a FinAC package. And once you get a FinAC package, the TCP connection terminates completely. So next time you'll have to send another, you again go through these 4 steps, and then you again get a FinAC package and your connection terminates, right? But in gRPC that doesn't happen. It is built on top of HTTP2. So what happens, you first build one connection between a client and a server, let's say. Here, client and a server is not the actual case, because this is basically you are calling a remote process. So between the client and a server, you establish a connection. This is a TCP connection that is established. To both of them, you give a protobuf. You tell the client that you have to send data in this format. You tell the server that you will receive data in this format. Then once you do this activity, then on the connection you are just sending messages constantly. And these messages are done in the protobuf format that you have predefined, right? And as a result, what your processing becomes faster. What we use is called bidirectional gRPC. Bidirectional gRPC is a representation of your sync calls, synchronous calls. Means you send, you also receive on the same channel, right? So the problem with bidirectional gRPC, as I said, is it establishes a connection and it doesn't terminate. It expects not to terminate. Now the Kubernetes load balancer this is how a typical pictorial representation, how your what was happening. A typical Kubernetes load balancer is once you establish a connection, it goes and finds a pod that it will send the traffic to, right? That connection is over, then it breaks the connection. Next time a request comes, it again goes and finds who to send this to. But when we said, okay, you establish a gRPC connection, all that the control plane was doing, it was only connecting to one of the backend or one of the pod and sending all the requests to that. And that's why we had this situation where all the traffic was going to only one pod, right? So how to solve with that? And this is a challenge if you will ever migrate to Kubernetes. This is what you have to be very cognizant of. Is Kubernetes will basically control your routing, and if you have any structure which is synced, for example, let's say you are having to connect to a DB connection pool. So what is a DB connection pool? A single connection is opened, that opens like 30 connections with it, then it distributes among your services, how you will use it. Will not work in Kubernetes. You'll have to do some engineering for it. And what kind of engineering, let's talk about. So what we wanted that when we send a request, whichever pod will be free, it should send the request to that. But in HTTP2, as I said, it will make a connection, it will not terminate it at all, unless you explicitly ask it to terminate. So what is the solution? How to do it? So the solution is, instead of making one connection, we said, okay, parallelly you open all pods and open one connection to it. So whenever we send a message, then you figure out which message queue is not full, just send to that. Am I clear over here? So instead of making one connection and sending it over there, we said to Kubernetes, or we put in something in between where we said establish connection to everything at all the times. Once you come up, once a pod comes up, have HTTP2 connection open. And so only task that will be remaining is, depending on our routing logic, depending on our balancing logic, we will just write the message to it. So that is how we try to solve it. We have currently done it using Envoy, because Envoy was a proxy we always used, and we use Envoy as a proxy because, as I said, we use a lot of encryption decryption logic. And if we had to copy this encryption decryption logic into every service, it is a lot of code repetition that was happening. So we wrote Envoy routines, which are basically assembler routines, web assembler routines. That's what we have written. And so anybody who is publishing a request or publishing a service to us, they do not have to copy this. They just copy the Envoy code and they can go live. But the way today we are establishing connection, we are using an Envoy load balancer instead of the Kubernetes load balancer. So Kubernetes load balancer APIs are consumed by Envoy. Then every time Envoy figures out a new proxy has started, the Envoy opens HTTP2 connection to it. So once we receive the request in Envoy is sending to the message queue that it wants. We are doing some new experiment with Linkerd. Linkerd is very similar to Envoy. It's a sidecar application, but Envoy has a little bit of limitation because Envoy has an injectable sidecar only. So its load balancing is also injectable. So every time you will have a pod, you will have to put it over there. Linkerd is completely cloud native. You can have a Linkerd instance running outside of your Kubernetes and do all this manipulation itself. So that is what we have been experimenting with, and the results are promising in one sense, where in Envoy what we were doing, we are having to configure the Envoy every time we had a new service. In Linkerd we are not having to do that. We are able to write one configuration, one YAML file, and that is able to control all these pods. But today this is not in production. This is something in works, and the reason we haven't pushed into production again comes back to some of the regulatory activities that we have. Anybody who understands PCI DSS? PCI DSS, have you heard of this term? Anytime you are collecting a card information from somebody to transmit payment information, you have to do PCI DSS. Now PCI DSS, you do an internal assessment. You also go to an external assessor who will basically come and investigate in your system that you are not saving any card data with you, right? Our existing system, and again, I may be digressing a little bit. The assessors will price you based on your computing nodes, right? So if you reduce your computing nodes, you will be reducing your prices. But if you bring in an extra system into it, if you bring in one extra server or extra setup that you haven't certified, you will again have to go and reassess the whole system. That's the reason we haven't rolled in this Linkerd into production. But in our staging today, this is working. This has made our life a little bit more easy. Thank you.